Good evening, everyone. We are moving to the next topic, electric potential and capacitance. We still have one more paper to be completed from Gauss's theorem. I'll come back and do it. Okay, right. So before we start, I'll tell you what we need in this chapter. Okay, there is something called electric field. Do you remember the concept of electric field? If you have a charge here, you can imagine a region. That region is called electric field, right? Just like the AC creates a cooling field inside this room, a charge creates an electric field around it. What is the meaning of it? If you put another charge inside this, that charge will be repelled. Am I correct? If you put something outside, nothing will happen. Okay. So electric field is that region inside which a force is felt by another charge. Right. So it is just like, I told you many times, when you are inside this room, there is cooling because AC is turned on here. Right. But when you're outside, you don't feel anything. No cooling at all. Because the effect of AC is confined within the walls of this room. Right. Same way, this is the region called electric field. Electric field. Okay. Any point outside is called infinity. Any point beyond boundary is called infinity. Okay. So let me repeat that point one more time. Just give me a second. One more time. Okay, look at this. This is the electric field. Electric field is created by a charge called source charge. Q, source charge, right? There is a region around it. This is known as electric field. Okay. Any point beyond the boundary is called infinity. Infinity. Okay. Infinity. So for infinity, you don't have to go to actual infinity. Infinity means any point beyond the boundary. Any point beyond the boundary. Now, all right. Good evening. All right. Just give me a second. Okay. So this is what it is. Listen, Rishi. Everyone. Right. So this is called an electric field. Okay. Any point outside the boundary is called infinity. All right. Now we're going to see something called electric potential. Electric potential. What is meant by electric potential? It is simply, for example, at this point, imagine a point here, and it is at a distance r from the charge. Okay. What is the potential at this point? It is simply the work done for what? Bringing what? +1 coulomb. Why +1 coulomb? The standard procedure is to take a +1 coulomb. That is called unit positive charge. Right. Work done to bring a +1 coulomb from infinity up to this point. Okay. Work done to bring a +1 coulomb from infinity up to the concerned point is called potential at the point. Electric potential. Electric potential. Okay. I'll calculate it now. I'll get a derivation for this. It's very important derivation. Okay. I repeat one more time. We learn about electric field here. What is electric field? Electric field is simply the region around a charge. Region around a charge inside which an electric force is experienced by another charge. Right. So to summarize it, if you keep something inside, there will be a force on it. But if you keep it outside, nothing will happen. Got it? And outside is called what? Outside is called by the name infinity. Infinity. Understood? All right, just keep that in mind. Now, we're going to find something called electric potential. Electric potential means what? It is nothing but, for example, electric potential at this point, at a distance r. What is it? It is the work done. Work done. Work done for what? Bringing what? +1 coulomb. +1 coulomb from where? Infinity. Up to where? Up to the concerned point. Potential at this point is what? Work done to bring a +1 coulomb from infinity up to that point. Potential at this location is what? Work done to bring a +1 coulomb from infinity up to that point. Potential at this location is what? Work done to bring a +1 coulomb from infinity up to that point. So basically, potential is the work done. Work done to bring a +1 coulomb from infinity up to the point. Got it? Now, just watch what I'm doing here. Look at this. I take an electric field here. This is an electric field. All right. I'll ask one of you to do this on board. Now, this is a charge. Okay. And right here, I consider a +1 coulomb, where at a distance of x. Okay, so what have I taken? I've taken a +1 coulomb at a distance of, tell me what, at a distance of x from the source charge. Got it? Now, is it inside or outside? It is inside the electric field. Got it? Okay, now look at this. Where is this force acting? Tell me the force. This plus is repelling this plus in the outward direction. Am I correct? Am I correct? Oh, tell me, positive would always repel positive. Am I correct? Positive would always repel positive. Am I correct? So this positive repels this positive outward with a force called F. With a force called F. Okay. And imagine we are moving this charge inward through a small distance dx. So I'll tell you the context one more time. What is the context here? We have taken an electric field, right? This is an electric field. Electric field is created by a charge, correct? And then inside, I'm putting a +1 coulomb. Where is it put? It is put at a distance of x from the source charge, correct? Correct. Then what? This plus is repelling plus in the outward direction, and you are displacing it. You are pushing it inwards. Through what distance? Through a small distance. Got it? Okay. What is the angle between them now? 180 degree, right? Force is outward. Displacement is inward. The angle between them is what? They are anti-parallel, right? Oh no, tell me what? The angle is 180 degree, right? So I'm going to write down the equation for work done. What is the equation for work done? Force dot displacement. Do you remember this? No. You know, work done, you learned this in lower classes, even in first year classes. Work done is given by force dot displacement, or that is equal to F into X into cos theta. What if it is small work done? It is dx, right? Small work done for a small displacement is dw is equal to F dot dx. dw is equal to F dot dx. So look at that. I am finding the small work done. What is the small work done? F, tell me what? F dot dx. Okay, what is it now? dw is equal to F into, tell me what? Dx into cos of 180. Why cos theta? A dot B is equal to, tell me Hasan, A dot B is what? A B cos theta. F dot dx is what? F dx cos theta. Right. Why 180? Because F is outward. Tell me what? Dx is inward. The angle is 180 degree. 180 degree. Got it? Let me complete this. I'll explain again. Don't worry. Okay. So I'm going to put F value. What is the force between these two charges? K into, do you remember Coulomb's law? Tell me, Dolly, K Q1 Q2 divided by R square. K Q1 Q2 divided by R square. K into, first charge is Q, second charge is 1 Coulomb divided by the distance between them is x square into dx. Am I correct? X square into dx. Am I correct? Into cos 180 is -1. All right. So look at that. That is equal to minus k into q into x square goes to numerator. What is x square going to numerator? X raised to, when something goes to numerator, the power becomes negative. X raised to -2 into dx. Last step. This is what have I done now? I have taken the small work done. Now tell me the obvious step. If you know the small work done, you will integrate to get the total work done, right? So I can find the total work done by integrating minus k into q into x raised to -2 dx. The last step, you can take the constants outside. Minus k into q into integral x raised to -2 dx. I'm doing it here. Integral x raised to -2 dx. There is a formula for integration. This is the formula you must have done many times in school. In first year classes, integral x raised to n dx. Do you know what it is? X raised to n plus 1 by n plus 1. Integral of x raised to 7 is what? X raised to 7 plus 1 by 7 plus 1. Integral of x raised to 9 is what? X raised to 9 plus 1 by 9 plus 1. Integral of x raised to 20 is what? X raised to 20 plus 1 by 20 plus 1. Got it? So, integral of x raised to minus 2 is what? X raised to, tell me what? X raised to minus 2 plus 1, minus 1. Minus 2 plus 1, minus 1. Okay. So, tell me what you're going to get. This is, tell me, I get the integration x raised to minus 1 by minus 1. Last step, I take minus outside. Minus or minus, tell me, that is plus kq into, what is x raised to minus 1? X raised to minus 1 is also called 1 by x. What have I found now? Work done, right? Work done, right? Now I'll put the limits. Look at the limits. I take it from infinity, I bring it to R. Because do you remember the definition? Work done to bring a plus 1 coulomb from infinity up to the point. Up to the point means somewhere here. To that point, the distance may be called R. Okay, so you are coming from where? You are coming from where? Infinity. So the lower limit should be infinity. You are coming to which point? This is my point. Where is that point? At a distance of R. So the limits are what? Infinity and R. Infinity and R. Here also infinity and R. Now, do you know how to give the limits? First, give the upper limit minus, tell me Nazia, give the lower limit. What is the upper limit? 1 by R. X in place of X, you put R, right? Minus lower limit is 1 by infinity. Any number by infinity will be 0. So finally, you get kq by R. What is this? Work done. Work done for what? Bringing what? Plus 1 coulomb. From where? From infinity to where? To the concerned point. Understood? One of the most repeated questions in this topic, in potential, you have only 2 derivations. This is the first one. It's a 5-mark question. Got it? Okay, it's a 5-mark question. Many times repeated in board examinations. There are 2 derivations. One is this one. Second one is potential due to dipole. Okay, electric potential due to dipole. Okay, I'll do it one more time. Do not worry. We'll keep doing until you are thorough with it. We'll go to the questions then. Okay, right. So basically, what is meant by potential? Potential is the work done. Potential at a point is the work done to bring a plus 1 coulomb from infinity up to the concerned point. Understood? Work done to bring a plus 1 coulomb from infinity up to the concerned point. How do we do this? Look at this. You consider an electric field. This is an electric field. All right. And at a distance x, you put a plus 1 coulomb. All right. Then what? This plus is repelling plus outward and you are moving it inward. Look at the angle. It is 180 degree, right? Then you can find the small work done. How to find the small work done? Work done is given by force dot displacement. So small work done is equal to Rishi. Small work done is given by force dot small displacement. So dW is equal to F into dx into cos theta. A dot B is AB cos theta. Correct? Cos 180. Then it is common sense you are putting force value. By Coulomb's law, what is force? K into Q1. First charge is Q. Q2. Second charge is 1. Divided by the distance square. The distance is x square, right? Into dx. Cos 180 value is minus 1, right? Okay. Then what? I write it as minus is written first. K, Q, x square is taken to numerator. That will become x to the power minus 2 into dx, right? Then this is the small work done. What is our intention? We need to find out the total work done, right? Okay, so how to find the total work done? If you know the small work done, you will have to integrate, right? So integral minus kq x to the power minus 2 dx. All right, I'll get all the constants outside. K comes outside, q comes outside. What is integral of x raised to minus 2 dx? X raised to minus 2 dx, x raised to minus 2 plus 1 by minus 2 plus 1. That's a standard formula. Okay, you have to learn this by heart. X raised to n dx is x raised to n plus 1 by n plus 1. Got it? Then what? Finally, minus will be taken outside. Minus of minus plus kq into x raised to minus 1 is 1 by x. 1 by x. Then I think of putting the limits. Where am I coming from? By definition, you should be coming from infinity. Infinity. All right. Up to where? Up to the point. This is my point P. All right. You're coming to this point, right? Infinity up to the point P. Got it? So you are finding potential at P now. So infinity, the lower limit is infinity because you are coming all the way from infinity. You are coming until where? Coming up to where? Coming up to the point P, right? Correct. Where is P? At a distance of R. So the lower limit is infinity, upper limit is R. Infinity and R. And you can put the limit, you put the upper limit first, minus, then the lower limit. Okay, 1 by R minus 1 by infinity. Any number by infinity will be 0. So finally you get KQ divided by R. This is the equation for electric potential due to a point charge. Got it? Got it. So now we will have potential difference, then equipotential surfaces, we will do questions. Okay, start writing. All of you understood? Everyone online? Yeah. So let us write. Right. Electric potential. First heading, electric potential. Right subheading, electric potential. Electric potential. You can write electric potential at a point. 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 Electric potential at a point in an electric field. Electric potential at a point in an electric field is what? The work done. For what? Bringing whom? Plus 1 coulomb. From where? From infinity to where? To the concerned point. Am I correct? Did you follow me? Tell me what? Okay, you can write potential at a point in an electric field is the work done. Is the work done. Potential at a point in an electric field is the work done. Is the work done in bringing a plus 1 coulomb. Potential at a point in an electric field. Potential at a point in an electric field is the work done. Is the work done in bringing a plus 1 coulomb. In bringing a plus 1 coulomb. In bringing a plus 1 coulomb from infinity up to the point. Okay. It is the statement I will repeat at least 100 times before board examinations. Okay, right. Potential at a point is the work done. Potential at a point is the work done to bring a plus 1 coulomb from infinity up to the point. Okay, infinity up to the point. Draw the figure. So this is the electric field which is created by a source charge. Which is created by a source charge. Okay. Okay. Created by a source charge. Now tell me the angle here. Tell me the angle here. This angle is 180, right? Put that angle as 180. Force is outward. Why is the force outward? This is positive. What you're putting is positive. Positive would repel positive, right? So this plus is going out and you are trying to push it in, dx. All right. Okay, small distance dx. Okay, and put our point here, P. That is where you are going to find the potential. It is where it is at a distance of R. It is at a distance of R. Okay. Okay. Now we can write, consider electric field Consider the electric field created by, a charge plus Q as shown. Consider electric field created by a charge plus Q as shown. Electric field created by a charge plus Q as shown. Okay. Electric field is created. Got it? And you're going to find the potential here, right? Okay. Now, next line. A plus 1 coulomb is kept. A plus 1 coulomb is kept at a distance. You are just writing whatever you see in the picture. That's it. Okay. You can write in your own words. But you always forget to write the introduction. That is why I'm writing. Okay, plus 1 coulomb is kept at a distance Ex from the charge. A plus 1 coulomb is kept at a distance Ex from the charge. Got it? That's all about the figure, right? Oh, tell me, how do you learn this? You just visualize the figure, then draw the figure, then write whatever you see in the figure. That's it. Got it? Got it? So you can write the small work done. We are finding the small work done first. The small work done for moving the plus 1 coulomb through dx. The small work done for moving the plus 1 coulomb through small distance dx. How do we write the small work done? Write the equation for small work done. Do you remember this? F dot dx. Don't ask me where it comes from. We learned this in last chapter, right? Work done is given by force dot displacement. F dot dx. dw. You call the work done by the name dw. Okay. dw means a small amount of work. Small amount of work. Okay. Force dot small displacement. Right? So let us expand it. dw is equal to, tell me, F into dx into cos 180. Do you understand how I got it? A dot B is equal to, tell me Vedant, A B cos theta. A dot B is what? A B cos theta. A dot B dot product. A dot B is what? A B cos theta. Right? F dx cos 180. Now let us keep going. Tell me what? What are you going to put? Force. Force value. What is force value? Coulomb's law. You have to use Coulomb's law, right? Right. K into Q. First charge is Q into second charge is 1 by x square into dx into cos 180 is minus 1. Cos 180 is minus 1. Okay. Tell me what you're going to get. Good evening, Vyom. This is what? Minus is coming here. Minus k. Q. X square goes to numerator. What is it? X raised to minus 2 dx. X square goes to numerator to become x to the power minus 2 dx, right? Now this is what? What I have done is the small work done, right? Right. Now what are we going to do? You will integrate, right? If you know the small work done, you can find the total work done just by integrating it. Okay. So you can find total work done. Total work done. Total work done W is what? Integral minus k q x to the power minus 2 dx. Where are you coming from? You're coming all the way from infinity, right? By definition, you know, potential is what? Work done to bring a plus 1 coulomb from infinity up to the point. Correct? So you're coming from infinity. You are coming up to where? Look at the figure and tell me. You are coming up to where? Coming up to the point P. Look at this. Where is P? At a distance R. Right? So you have to put the limits. You are coming from infinity. You are coming up to a distance R. Got it? So let us get the constants outside. Minus K comes outside. Q comes outside. do the integration on the margin. This is the standard formula for integration. Integral of x raised to n dx is x raised to n plus 1 by n plus 1. So write it there. I have taken integral of x raised to n dx, which is x raised to n plus 1 divided by n plus 1. What is integral of x raised to minus 2? X raised to minus 2 plus 1 divided by minus 2 plus 1. Right? In place of n, look at this. In place of n, I have minus 2. So n plus 1 becomes minus 2 plus 1. N plus 1 becomes minus 2 plus 1. Correct? So that will be x raised to, what is this? Minus 2 plus 1, minus 1. Minus 2 plus 1, minus 1. Correct? And what is this now? X raised to minus 1 is called 1 by x, right? So that gives you minus 1 by x. Got it? What happened then? Tell me. Should I repeat? Okay. So this is minus 1 by x. I am putting it here. The last step now, tell me what? The last step is what? That is equal to minus kq into, minus is taken outside, plus into 1 by, in place of x, put the upper limit, or minus 1 by lower limit, infinity. Infinity, that is 0. Any number by infinity will be what? Any number by infinity will be 0. Okay, so that part will vanish. What do we get now? This is kq by r. This is actually what? Work done. For what? For bringing what? Plus 1 coulomb. From where? Infinity. Up to where? Up to the point P. Am I correct? Work done in coming from infinity up to the point P is called potential. So this is the expression for potential. We can finally write it as kq by r. Write it. 1 by 4 pi epsilon naught into q divided by r. 1 by 4 pi epsilon naught into q divided by r. Who will need repetition? Okay, right. So we have learned the equation for potential. Now this is a very important question. Look at this. Potential is given by kq divided by r. I told you the definition. It is the work done to bring a plus 1 coulomb from infinity up to the point. Okay. First of all, is it a scalar quantity or a vector quantity? Potential is always a scalar quantity. Scalar quantity. Potential has no direction, but electric field is a vector quantity. It's a repeated question. So many times this question has come. Potential. What is defined electric potential? Is it a scalar quantity or vector quantity? It's always a scalar quantity. No direction for potential. Okay. Electric potential is a scalar quantity. What is the unit of it? Unit of electric potential is volt. Volt. Okay. For example, for a cell, you know, you have cells here, right? Battery, the cell. We say cell potential is 1.5 volts, right? So potential is basically measured in volts. Volts. The unit of potential is volt. Okay. And this is point number 1. Point number 2. What is potential at P? It is the work done. Tell me, work done in bringing a charge from infinity up to the point. Am I correct? Am I correct? Divided by Q. Work done per charge. Why per charge? Because you brought home plus 1 coulomb, right? Oh no, look at this. You know, what is, I'm writing the definition of potential at P. What is the definition? What is the definition? It is the work done. Am I correct? You are coming from where? You are coming from where? Infinity. So suffix infinity. Up to where? Up to the point P. Am I correct? You are bringing what? Plus 1 coulomb. So plus 1 means per charge by Q. So basically, this is how you write the potential at P. Potential at P is work done from infinity up to P divided by Q. So there is another unit here. What is the unit of work? Joules. What is the unit of charge? Coulomb. Joule per coulomb is also called volt. Joules per coulomb is also called volt. That is second point. Let me complete this. Third point. This is so important. It is given in the reader. Electric field proportionality is 1 by r square. Potential proportionality is Tell me. 1 by R. Am I correct? Electric field potential. Electric field is what? Do you remember the equation for electric field? KQ divided by R square, right? Electric field is KQ divided by R square. Electric potential is what? KQ by R. Both have inverse proportionality, right? They will ask you to draw this graph. It is drawn as 2.1, figure number 2.1 on the reader. It is so important. Trust me, it has come many times. This is how you draw the graph. E here, E or V. E or V on y-axis and R on x-axis. If you draw, both the graphs will be rectangular hyperbola like this. Trust me, if you draw the graphs on different plots, you won't get marked. 100% sure. You have to draw both the graphs on same plot, same graph. All right. Then how do you differentiate between them? Which one is E, which one is V? That is the tricky part. I'll tell you here, E is proportional to 1 by R square. V is proportional to 1 by R. Who has greater power? E, right? Greater the power, steeper the curve will be. Steeper the curve. Steeper means what? You imagine you are climbing up along the path. You are climbing up along this path and this path. You find which one more difficult? Which one more difficult? This one or this one more difficult? This is more difficult to climb, right? Right. Imagine you are just climbing up on this path. You are climbing up on this path. Which is more difficult? Imagine you have a bridge. You know, this is where you enter the bridge. The bridge is like this. Another bridge is like this. Which bridge is actually difficult to climb up? It's second one, no? That's steeper, right? Correct. So steeper one is always for which graph? The one with greater power, steeper one. So look at these graphs. Out of these two, this is steeper, much steeper than this one. This is more flat, right? So steeper one should belong to the greater power. Who is greater power? R square, right? The other graph should be potential. It is one of the most important questions in first part of the reader. All right. You just have to draw the graph, but many people will lose the marks. Understood? Because you should know how to. One thing is, both should be drawn on the same graph. Another frequently asked question in DPS papers, it's very important. V and D graph. Okay. Both should be drawn on the same graph, same plot. Okay. V and D. I'll do it again. Don't worry. And the fourth one, hope you remember this question. I'm drawing V against 1 by R. V against 1 by R. This is V. This is 1 by R. Do you remember a similar question in electric charges and fields? V again is 1 by R. How will you do it? Here, who is on y-axis? V is on y-axis. Who is on x-axis? Who is on x-axis? No, it's not like this. This is R on x-axis, right? But here it is who on x-axis? 1 by R, no? So 1 by R should be taken as a single thing, single entity. So it is like direct proportionality, right? This is on y-axis, this is on x-axis. It is direct proportionality now. So the graph will be what? The graph will be a straight line. I'll draw two graphs this way. Do you remember having seen something like this? We did this in class. All right. This charge must be positive. They'll ask you to identify the nature of charges. This charge is positive. Ask me why. Ask me why. Because there are 4 quadrants. This is called quadrant number 1, quadrant number 2. This is 3. This is 4. I had told you that this quadrant is positive. This quadrant is negative. Correct? Because this is positive y-axis, right? This is negative y-axis. So here, if you draw the graph, that is positive voltage. Positive voltage is created by positive charge. Positive potential is created by positive charge. Negative potential is created by negative charge. So how do they ask the question? They will give this graph and it is there in the worksheet. I'm going to give you the worksheet now. Okay. So this identify the nature of charges and explain why. Okay. Now, why is this positive? Here I would say that this charge is positive. Why is that positive? Because the graph is in positive quadrant. What about this one? This is negative. Why is it negative? Because the graph is drawn in negative quadrant. Am I correct? Am I correct? All right. So I'll explain one more time, then we will write this. Okay. Look at this. This is what I have written so far. I'm going to do this one more time. Okay. Look at this. First thing. What is potential by definition? Potential by definition is work done. Potential at P is what? Work done, Rishi, please for God's sake. Potential is what? Work done, right? Work done to bring a +1 coulomb from infinity up to the point. Okay, work done from infinity up to the point P per charge. Per charge. Why per charge? Because you are bringing 1 coulomb, +1 coulomb, right? +1 coulomb. Got it? And what must be the unit of this? Tell me. Work is measured in joules and charge is measured in coulomb. There is a simpler unit called volt. Okay, volt. Volt is the unit of potential. Then I told you, potential is a scalar quantity. Scalar quantity. Potential has no direction. Potential has no direction. All right. Then we learn what? Potential unit we wrote. Potential is a scalar quantity. Equation for potential we derived just now. Do you remember it? 1 by 4 pi epsilon 0 into 1 by 4 pi epsilon 0 into Q divided by R. 1 by 4 pi epsilon 0 Q by R. That is KQ by R, right? Then we wrote the proportionality graph. Okay, proportionality graph. How do we draw the graph? I told you this is an important question. Electric field proportionality is 1 by R square and potential proportionality is 1 by R. Who will be steeper? Who will be steeper? The greater the power, steeper the graph is. Greater the power, steeper the graph is. Got it? So if it is R cube, that will be more steep. Again, R raised to 4. I can draw the graphs. 1, 2, 3, 4, 5. This will be 1 by R. 1 by R square. 1 by R cube. 1 by R raised to 4. 1 by R raised to 5. Understood? As the power increases, it gets more and more steep. That's it. Got it? All right. So I can draw both the graphs. I can draw both the graphs here. Look at the graph. This is how you draw the graph. Here I'll take E or V. I'll take E or V on y-axis, E or V on y-axis. Very, very important in your school examination also. E or V on y-axis, R on x-axis. Okay, R on x-axis. What kind of proportionality? This is how you draw the first one, and this is how you draw the second one. All right. Okay, who is steeper out of these? Steeper, second one is steeper, right? More steep, right? All right, that should belong to the higher power. Who is higher power? E, right? So this graph must belong to E and this graph must belong to V. All right. Steeper the curve, you just try to visualize. Imagine that you're climbing up. You will obviously find difficult to climb this. All right, that's vertical, right? That's more steep, right? So that is E, the other one is V. All right, this graph is important. Make sure that you draw both on the same graph. And then the last thing I told you, that is V against R. What if V against 1 by R is asked? V against 1 by R. Proportionality is the same, but look at this. I'm going to take these guys together. This is V, 1 by R together. V is on y-axis, 1 by R is on x-axis. So what kind of proportionality? Direct proportionality, right? So if you draw V against 1 by R, this is so important. Even in many chapters, the same concept will come. Okay. If you draw against 1 by R, this is how the graph would look like. This is V here. This is 1 by R here. Graph is here. Graph is here. This is drawn here means what? Here the potential will be, tell me, potential is positive. Why is it positive? It is drawn in the positive quadrant. Correct. If positive potential means charge is also positive, that is common sense. Positive charge creates positive potential. Negative charge creates negative potential, right? And what about this graph? Here I can say V is negative. Potential is negative. Potential is negative means charge is also negative. Then there is one more question coming up. Which charge is greater? How do you identify? Do you remember something? Greater the angle. Do you remember? Not at all. Greater the angle, greater the slope. Greater the slope, greater will be the charge. So how do you identify that? Hope you remember that. Look at this. If this angle is theta, if this angle is 3 theta, that means potential of this case is 3 times as much as in the first case. If this angle is 4 theta, tell me what? Potential here is V, potential here is 4V. If the angle is like 7 theta, tell me what? 7V, that's it. Understood? So just look at the slopes. That will tell you about what? The magnitude of charges. That is also a previous question. All right. So you can identify the nature of charges from the graph. If you listen to me properly, you're never going to forget it. Okay. So first thing is what? First thing is that the graph is going to be a straight line. Secondly, this is positive graph, which means potential is positive. Potential is positive means charge is positive. Okay. Here potential is negative. That is charge is negative. That's common sense because it is positive y-axis. This is negative y-axis, right? And how do you identify the size of this? Which charge is more? Which charge is more? Greater the angle. Look at that. This angle is theta 1. This angle is theta 2. Which is more? Theta 2 is more. Theta 2 is more means you can even say, I'm writing it here. Theta 2 is greater than theta 1 means potential for 2 is greater than potential for 1. Got it? The greater the angle, the greater will be the potential. All right. So potential is more when charge is more. Okay. When you have a bigger AC with higher tonnage, like this is like 2 ton AC. If you're putting like 3 ton AC, there will be more cooling, right? Correct. Correct. If you put like 10 ton AC, there will be more cooling, more and more cooling, right? As you increase the weight, tonnage of the AC, cooling will increase. Same way, potential will increase when the charge is more. Got it? Q2 greater than Q1 means V2 greater than V1. Got it? Write this down. All of you got this? Everyone understood? Now there is one more point I wrote. Look at this. Look at this. You know, how do you identify which charge is bigger out of these? Now look at this. This is how you find it. When you look at this, hey, please. Look at the angles. The greater the angle, see the angles? Here from the figure, theta 2 is greater than theta 1. Second angle is greater than first angle. If this angle is greater, you can say slope is greater than, slope for 2 is greater than slope for 1. Slope means tan theta. So just notice this is having a smaller slope, whereas this is having a bigger slope. All right. The greater the slope, the greater will be the potential. Greater will be the potential because the slope is actually giving you the potential. Okay, so if the slope is greater, potential also will be greater. And greater potential is created by which charge? Greater charge Q2 will be greater than Q1. Q2 second charge will be greater than first charge. Understood this? Write this also as a note. Now let us move to the paper. This is paper number 1. There are 2 papers for potential alone. Okay. First one, question number 1, define electric potential. All are previous board questions, okay? 31 or something, 31 questions are there. Question number 1, define electric potential. Is it a vector or a scalar quantity? Tell me, potential at a point is the work done to bring a +1 coulomb from infinity up to the point. Okay, it's a scalar quantity. You know it's a scalar quantity, right? Okay, question number 2. Draw a plot showing variation of electric field and electric potential with the distance due to a point charge. You have to draw this graph. Draw this graph. Question number 2. Draw a graph of, what is the question? I told you, you have to draw both on the same graph. Got it? Never draw them separately. You won't get even half mark. Okay. So, read question number 2. Draw the graph showing 7 or 8 times asked in the last 10 years. Okay. Draw a graph showing variation of electric field and potential with the distance r due to a point charge. Okay. And you write this. You better write this explanation also, because later on when you see, otherwise you won't understand. Okay. The steeper the graph, or the more the power, the steeper the graph. Okay. When the exponent increases, the steepness increases. Exponent increases, steepness increases. It is actually the figure number 1 on reader, chapter number 2. All right, 2.1, figure number 2.1 on the reader. Okay. Steeper one is always the one with the greater power. Steeper one is always the one with the greater power. That is electric field. Electric field has greater power, so it is steeper. Okay. The other one is less steep. All right. Okay. Moving to question number 3. This is the question I was talking about. All of you online understood this? Question number 3. The two graphs drawn here show the variation of electrostatic potential with 1 by R for 2-point charges Q1 and Q2. What are the signs of the charges? Can you tell me the signs of the charges? Q2 is what? Q2 is drawn in the positive side, right? Positive quadrant. Am I correct? Am I correct? Look at the graph. Question number 3. Draw the graph. I'll tell you. Question number 3. Draw the graph. Draw the graph like this. It is given. This is one of the charges, one of the graphs. Here they have taken V. Here they have taken 1 by R. Okay, it's V again is 1 by R graph. They have given you two graphs. One for Q2. Oh, this is Q1. This is Q2. All right. Okay. Now, what is the question? Question number 2. Question number 1. What are the signs of the two charges? Which of the two charges is larger in magnitude and why? We have done this already, right? Okay. How to identify the signs? This is in the positive quadrant, right? Positive quadrant. This is called positive quadrant. This is called negative quadrant. Okay. Got it. So you can write, let us call this graph by the name 1. This graph is 1 and this graph is 2. You can write right now. Graph 1 is drawn in the positive quadrant. Quadrant means that segment. This part, yeah. This part is called positive quadrant. Okay. First quadrant is called positive quadrant. Okay. Graph 1 is graph 1 is drawn in positive quadrant. Okay. Therefore, V2 is positive. Potential due to it. Potential for this one is positive. Right? Correct. If that is drawn in positive quadrant, that means potential is positive. Correct? Potential is positive means what? That charge is, tell me what? Positive. Understood? So we know that Q2 is positive. Got it? Understood? Simple common sense. Now, how about the other one? Graph 2. Write it yourself. Graph 2 is drawn. You have to learn every single question I give in class. All right. Do not trust what is done in your school. They'll teach something, but they'll ask something else in school examination. Understood? Right. That's what. Okay. Graph 2 is drawn in the negative quadrant. Graph 2 is drawn in the negative quadrant. Graph 2 is drawn in the negative quadrant. Therefore, V1 is negative. V1 is negative. Okay. V1 is negative means what? If potential is negative, even the charge is also negative. In the first part of the question, they were asking you to get the signs of the charges, which we have done. Hope you all got it. All of you got it? Got it? Right. Now, second part is what? Tell me, Anushka. Which of the two charges has larger magnitude, right? Which of the charges is bigger and why? They are asking bigger and why. Listen, please. Listen to me. This angle you call theta 2. This angle you call theta 1. Okay. So, let us write part 2 of this question. Part 2 of this question. I'm writing it here. Part 2. Right. So, theta 2 is greater than theta. Oh, sorry. Theta, don't talk, please. Theta 1 is greater than theta 2. Am I correct? Theta 1 is greater than theta 2. Look at the figure and tell me. Angle is more in the second case, right? First case, right? Theta 1 is more than theta 2. Which means slope of 1 is greater than slope of 2. More theta means more slope. Okay. More theta means more slope. Theta 1 is greater than theta 2 means slope of 1 is greater than slope of 2. The more is slope, the more will be the potential. V1 is greater than V2. Okay. When is potential more? When the charge is more. When is cooling more? When the AC has more weight, right? More tonnage, right? More capacity. So more is the voltage when potential when more is the charge. So I can conclude that Q1 is bigger than Q2. Got it? Q1 is bigger than Q2. All of you online understood this? One more question, we'll take a short break. Question number 4. Can you read question number 4? 4-point charges are placed at the corners of a square in 2 ways. Will the electric field and potential at the center be the same or different in 2 configurations? Why? I'll do a thing here. Look at this. Look at this. I'm going to take 4 cases. They have given only 2. I'm going to tell you all the 4 cases. Okay. Listen to me. Listen to me. First and second I'll do. Third and fourth Hassan will do. Okay. Now look at this. Look at this. I have like 4 squares. See the squares? Square number 1. This is square number 2. Let us do 2 by 2. Okay. Right. 2 at a time. Now this is my first square. Right. First square. Right. Okay. So I got see the configuration. I'm going to put a plus Q here. I'm going to put a plus Q here. Another plus Q here. And a 4th plus Q here. Okay. Now look at this. See carefully. I'm going to find the electric field here. What is the standard procedure? Put a plus 1 coulomb, find the force on it, right? Put a plus 1 coulomb, find the force on it. Look at this. I'm putting a plus 1 coulomb. And I'm going to see where it is moving. See my finger moving now. Look at this. This plus is repelling this plus in this direction. Am I correct? Am I correct? Am I correct? Look at that. This plus is repelling this plus in this direction. Similar way, this plus is repelling this plus in this direction. Am I correct? Am I correct? Look at that. This plus is repelling plus in this direction. This plus is repelling plus in this direction. Similar way, this plus is repelling plus in this direction. Okay? In this direction. Whereas, tell me what? This plus is repelling this plus in this direction. Tell me about it now. All forces are equal. Imagine I'm standing here and 4 guys are pulling me in 4 directions equally. What is the net force on me? 0. So electric field will be what now? Electric field is equal to 0. But look at the potential. Look at the potential. Look at this. Look at this. Please, please, please. First potential due to the first one. KQ by R. KQ by R, right? R is the distance here. Potential due to the second one. KQ by R. Potential due to the third one. KQ by R. Potential due to the fourth one. KQ by R. Will it have a chance of becoming 0? No. All are positive, right? KQ by R plus KQ by R plus KQ by R plus KQ by R, 4 KQ by R, right? So I can say potential is not equal to 0. Correct? So in this case, electric field is 0. Potential is not equal to 0. Now let me do the second one. You will understand. This time you will understand. Don't worry. I am finding about this case. Plus Q I am putting here. Minus Q I am putting here. Plus Q here. And minus Q here. Tell me what? How do I find the electric field? How do you find the electric field? Put a plus 1 coulomb like all times, right? Correct. Then what? Put the plus. Tell me this plus is. Tell me this plus is repelling this plus in this direction, right? Correct. Okay. Now tell me this minus is attracting this plus in this direction. Am I correct? Now this plus is repelling this plus in this direction. Am I correct? Tell me, it's common sense. Minus Q is subtracting this plus 1 in this direction. Tell me about the forces. They are all equal and opposite, right? Correct. They are all equal and opposite. Tell me what you're going to get. Electric field is equal to 0. They are going to cancel out, right? Correct. Now tell me about the potential. First one's potential. KQ by R plus. Second one's potential. Minus KQ by R. Because I already told you, negative charge creates negative potential, right? That's common sense. Tell me next one, third one, KQ by R plus fourth one, minus KQ by R. This gets cut with this gets cut with this, and you're getting what? V is equal to 0. So we have done 2 configurations. Now E is equal to 0, V not equal to 0. E is equal to 0, V is equal to 0. Then 2 more are possible. V equal to 0, E not equal to 0, V not equal to 0, E not equal to 0. Actually, they have asked only 2. I'm doing all the 4 possible cases. Got it? Now they can ask one more question this way. Now, can we have E is equal to 0, V is equal to 0 case? Can we have E is equal to 0, V not equal to 0 case? Can we have E not equal to 0, V equal to 0 case? Can we have E not equal to 0, V not equal to 0 case? All are possible. All are possible. Understood at a point? Electric field can be 0, potential can be 0. Electric field can be 0, potential can still remain non-zero. Electric field can be non-zero, potential can be 0. Got it? Electric field and potential can be non-zero. All four possible cases I can draw now. Now, this is the first case. I don't know which one is asked in the question, but once I've done this, you can try that as homework. This is easy. All right. Okay, try to have the idea. It is finding electric field. How do you do that? You put a +1 coulomb, right? And then see the directions. Okay. And for potential, you directly add the equations. That's it, because it's a scalar quantity. You don't have to put the direction, right? I said potential is a scalar quantity. Scalar quantity, right? Scalar means I don't have to put direction. Just put the potential. KQ by R, KQ by R, KQ by R, KQ by R. Here, KQ by R minus KQ by R, KQ by R minus KQ by R. Don't say that minus is direction. That minus is actually sign of the charge. Got it? Potential is a scalar quantity. Okay. So let us do all the possible cases as question. Okay. Write it as a note. Start writing, all of you. Everyone online understood this? Just draw both the figures. We will do together. All of you online understood this? Tell me, please. Right. So first of all, you have to put a +1 coulomb here. This is +1 coulomb. Next class we'll almost finish potential part. Okay. Capacitance is also easy. We will do the theory part. Will finish very quickly. Then we will focus more on questions. Okay. Right. Plus Q, plus Q, plus Q, plus Q, first one. And now question is different. That's a homework for you. Okay. I'll do all the 4. And those 2 will be any of these 4. Got it? Got it? Okay. So put the +1 coulomb and see the directions. Draw the direction. Tell me. Try to. This plus is repelling plus in this direction. Okay. In this direction. Now this plus is repelling this plus in this direction. Similar way, this plus is repelling this plus in this direction. And this plus is repelling this plus in this direction. Imagine a person is surrounded by 4 guys and they are pulling him in all directions, right? They are pulling him equally in all directions, right? So you can find electric field. You can write the electric field as 0. Potential is what? Potential is given by 4 people around, right? As in, if I take the phone, you won't get it back. KQ by R plus KQ by R plus KQ by R plus KQ by R. So there are 2 potentials, right? 4 potentials, right? One given by the first one KQ by R, second one KQ by R, third one KQ by R, fourth one KQ by R, right? So altogether it is 4 KQ by R, which means it is not equal to 0 anyways, right? Correct. Potential is not equal to 0. So we have a first case. Let us rewrite it. E is equal to 0, V not equal to 0. How do they ask the question? They'll say like, can we have a situation where the electric field is 0, but potential still remains non-zero? Yes. Then illustrate. You have to draw this figure then. Got it? Or they'll give you the figure and then ask the conditions. Okay. Now, tell me about the second case. This is the first case done, okay? Second case, right in the middle, you are going to put a +1 coulomb and see what's happening. Tell me, see what's happening. Tell me, Halima. This plus is repelling plus in this direction. Okay. This minus is attracting plus in this direction. This minus is attracting plus in this direction. Right. Okay. And the last one, this plus is repelling plus in this direction. Okay. So in all directions, again, equal forces acting, right? If you didn't understand, please feel free to tell me. Okay. Plus repels plus right downward, minus attracts plus upward. This plus repels plus upward, minus attracts plus downward, right? Electric field will be what? Electric field will be equal to 0. All are cancelling out. What about potential? Potential is KQ by R. First one is plus. minus k q by r. Second one is minus. Plus. Third is k q by r. Plus. Last one is minus k q by r. Plus k q by r minus k q by r plus k q by r minus k q by r. That is 0. So you can finally write electric field is what? Electric field is equal to 0, even potential is equal to 0. Electric field is 0, potential is 0. Just draw the figure, we'll take the break. Just draw the third case and fourth case. Draw the third case. I'm drawing the third case now. Now this is plus q. Here it is minus q. We will do this after break. Both are minus q. This is case number 3. Case number 4. This is like, I'll give you all the values. Here it is plus 2q. Here it is plus 3q. Here it is plus 4q. So we have done two cases, E is equal to 0, V naught equal to 0. And then E is equal to 0, V is equal to 0. Got it? Okay. We'll take a short break and come back. Now let us do the third question. Now write this. This is third configuration, right? What are we going to do? You will put the plus 1 coulomb in the middle. Write it, plus 1 coulomb. Tell me what's happening. This plus repels plus in this direction. Am I correct? Plus in this direction. Plus is repelling plus in this direction. Right. Plus is repelling plus in this direction. Okay. That plus is repelling. Tell me. That plus is repelling plus in this direction. All right. So there are two of them, right? Now what? Now what is this minus doing? This minus is attracting this plus in this direction, right? Minus is attracting plus in this direction. I'm using another color here, okay? Right, to represent that force. That is down. Again, what is this minus doing? That minus is also, tell me, attracting it towards it. So tell me now, look at the forces. These are the forces. Now, will they cancel out? No. So they have a net force, right? You can even complete the parallelogram, draw the diagonal. That is the direction of force, right? How do you find the direction of force? Complete the parallelogram, draw the diagonal. That is called parallelogram law of vector addition, right? But anyway, that is not needed. Just know that electric fields won't cancel out, right? Electric fields won't cancel out. They are not in opposite directions anymore, right? Electric field due to this charges in this direction, due to this charges in this direction, due to this one is this way, due to this one is this way. So together they are downward, right? Okay, so I can say electric field is not equal to 0. Now write the potential. What is the potential due to first one? KQ by R plus. What is the potential due to second one? KQ by R. What is the potential due to third one? Minus KQ by R. How about the potential due to fourth one? Again, minus KQ by R. KQ by R minus KQ by R, KQ by R minus KQ by R. That's going to give you V is equal to 0. Correct. Got it, all of you? So what can we say? Electric field is not equal to 0. Electric field is not equal to 0. Potential is equal to 0. So far, we have done 3 configurations. E is equal to 0, V is equal to 0. E is equal to 0, V not equal to 0. E not equal to 0, V equal to 0. Let us do the fourth configuration. Okay. Now, tell me when you are done. Finish this. E not equal to 0, V equal to 0, right? Fourth one, you can put a plus 1 coulomb here. You can put a plus 1 coulomb here, right? Tell me what? Right. Put a plus 1 coulomb. Tell me what now? Let us draw each force one by one. Tell me what is this plus Q doing? Look at this. Plus Q is repelling plus 1 in this direction. Plus Q is repelling plus 1 in this direction. Plus 2Q is repelling plus 1 in this direction with double the force. Why double the force? If charge Q creates E field, 2Q would create 2E field. Am I correct? Now, how about the third one? This third 3Q. 3Q is creating what? It is repelling with 3 times force. Am I correct? 3 times force. Look at that, 3 times. That force is 3 times this time. And look at the fourth one. 4q is repelling with 4 times force. Now they are never going to cancel, right? Now these forces will never cancel, right? So I can say electric field is not equal to 0. Correct. How about potential? How about potential? Potential, first one, kq by r plus. Second one, k into 2q by r plus. Third one, k into 3q by r plus k into 4q by r. Will they have a chance of cancelling out? No, all are positive, right? All are positive means V not equal to 0. So we have the last case here. Look at the last case. This is E not equal to 0. V not equal to 0. E not equal to 0. V not equal to 0. So we have done all the cases. Question number 4 is somber for you now. Try that yourself. Okay. I'll introduce a new topic and wind up. Okay. All of you got this? Everyone? Oh. I'm repeating this one last time. All of you online got this? I'll explain one last time very quickly. So look at this. This is third case. Now for the latecomers, I'm repeating. In this case, you are putting the plus 1 coulomb. Look at this. Look at that. This plus is repelling plus downward. Okay, this plus is repelling plus downward. This plus is repelling plus downward. They are the green arrows. Got all right. Got it. This plus is repelling plus downward, the green arrow. This plus is repelling downward. That is also green arrow. What is the minus doing? Minus is attracting plus downward. That is the orange arrow. Got it? And this minus is also attracting it towards it. Now, will they cancel out? No, 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 no. They are in opposite, not in opposite directions, right? Okay, they have a net field. How do you find the net field? Complete the parallelogram, draw the diagonal, right? The net field is down. Can they cancel out? No. They can cancel out only if they are in opposite directions. Right? Imagine I'm standing here. Halima is pulling me towards her and Vedant is pulling me towards him. Now then what? Now I'll definitely move in this direction, right? Right. I'll be moving in this direction. Right. So here these won't cancel out because they are not acting in opposite directions. Correct? They are not cancelling out. So electric field won't be 0. How about potential? K into plus Q by R, K into plus Q by R, K into minus Q by R, K into minus Q by R. All will cancel out, eventually giving you what? V is equal to 0. So E not equal to 0, V is equal to 0. How about the fourth case? Look at this. I put plus Q here, plus 2Q, plus 3Q, plus 4Q. Tell me what? Plus Q is repelling plus 1 in this direction. I can call the electric field as E. Plus 2Q is repelling in this direction with intensity E. Why 2E? Why is it 2E? Because Q charge gives intensity E, 2Q charge gives intensity 2E. Correct. What about 3Q then? 3, 4Q then? 4E. Correct. So this 3Q is repelling with 3 times C and 4Q is repelling with 4 times C. That is why they are of different sizes, right? Correct. Now they can't cancel out. Am I correct? Correct. Look at this. The electric field won't be the same because the charges are not equal. This is pushing this up. This is pushing this up stronger. This is pushing this down and this guy is pushing this down. They won't cancel out. Electric field won't be 0. Potential also won't be 0 either, right? Correct. Why? First potential is KQ by R. Second potential is K into 2Q upon R. Third one is K into 3Q over R. Fourth one is K into 4Q over R. Right? Positive, 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 positive. None of them is negative. Correct? Correct. So all positive means they will never ever cancel out, right? So potential won't be 0. Electric field won't be 0. Potential won't be 0. So we have discussed all the 4 cases. E is equal to 0. V is equal to 0. E is equal to 0. V not equal to 0. E not equal to 0. V is equal to 0. E not equal to 0. V not equal to 0. Understood? All the 4 configurations are possible. Got it? Any questions here? Tell me that. Which part? Right. Okay. So this case is very important. E naught equal to 0, V equal to 0. Here it is E naught equal to 0, V naught equal to 0. Just write a heading. Write heading potential difference. Potential. I'll just introduce. I'll wind up for the day. Potential difference. Potential difference. Just 2-3 minutes. Close your book. You don't have to write it. I'll just explain. Okay. I'll just start off. Close your book. Listen here. Okay, right. So listen everyone. Potential difference. Okay, I told you about potential. Look at this. I told you about potential. You know, I have a charge here, which is called the source charge. What is the potential at this point? It is the work done. Tell me please. Work done in bringing a +1 coulomb from infinity up to the point A. Am I correct? What is the potential at B then? Work done in bringing a +1 coulomb from infinity up to the point B. Okay. Their difference of potentials is known as potential difference. I am writing it. Look at this. VAB is given by VB minus VA. Potential difference between A and B is equal to potential at B minus potential at A. I'll tell you what it is. It is actually WAB divided by Q. I'll tell you what it is. I repeat one more time. What is potential? It is the work done in transferring a charge from infinity up to the point. Potential at A is what? Work done in moving a +1 coulomb from infinity up to A. What is potential at B? Work done in moving a +1 coulomb from infinity up to B. Their difference is called potential difference. And you can prove that it is the work done in transferring a charge from A to B. Okay, but I'll repeat one more time. Potential at B minus potential at A will be same as what? Work done in moving a charge from A to B. Work done in moving a charge from A to B per charge. Why do I put per charge? Because all the time I put +1 coulomb. I move +1 coulomb, right? Oh no, I repeat. Okay, so look at this. I repeat one more time. There are 2 points I'm considering now. Please, it's important. They'll simply say WAB by Q is equal to VB minus VA in school. But you should have an idea about it. Understood? Otherwise, the question will be difficult. Okay. Look at this. What is potential at A? Potential at A means it is the work done in moving a +1 coulomb from infinity up to A. What is the potential at B? Work done in moving a +1 coulomb from infinity up to B. Got it? So I can say, what is potential at A? Potential at A is work done in moving a charge from infinity up to A. Am I correct? Am I correct? Work done in moving from infinity to A per charge. Why per charge? All the time you bring home +1 coulomb, right? Correct. And what is potential at B now? Can you tell me what is potential at B? Potential at B is equal to W infinity B by Q. Correct. I've just written the mathematical form of the definition. What is the definition again? Work done. This is the 100,000th time I'm telling you. Tell me. Work done to bring a +1 coulomb from infinity up to the point. Got it? Infinity up to A. Now I'm telling you about potential difference. Potential difference VAB. What is potential difference between A and B? It is VB minus VA. Potential at B minus potential at A. And you can show that which is not needed. Okay, you can show that it is the work done. It is the work done in moving a charge from A to B. Which charge? +1 coulomb. Work done in moving charge from here to here minus work done in moving a charge from here to here is same as work done in moving a charge from here to here. Got it? Oh no, work done in moving a charge from here to A minus work done in moving a charge from here to A is same as work done in moving a charge from A to B. Okay, so finally I can have my equation. How do you define potential difference? WAB divided by Q. This is the definition of potential difference. This is the definition of potential difference. Next point we have is equipotential surface. 100% sure there will be a question in first term examination. I'm not saying a 99.99, 100%. Okay. And I'll give you 5 questions from equipotential surfaces. One of those questions will come for sure. Okay. Equipotential surface. All the previous questions I'll do. Okay. Equipotential surfaces. Equipotential means potential will be equal everywhere. Such a surface is called equipotential. We'll see that in the next class. All these things clear? Shall we wind up for the day?